Hello and welcome to College Algebra Section 1-1. So we're talking about graphs of equations today. So let's get into it. So equations are often in two variables, of course, with y and x, or y with respect to x. We treat x as our dependent variable and y as our, x is our independent variable and y is our dependent variable. We often write them in ordered pairs. Remember, please, that ordered pairs are always x comma y. And the collection of all solution points creates a graph. So if I have something like this, I would plot it as such, 2, 13. So, 1, 2, 13. I go up to 33, so I'm going to go by, 5 sounds good? So 5, 10, 15, 20, 25, 30, 35. And we'll just go by ones here in this direction. 3 to 4. 3, 4, and over to about -1. Okay, so 2, 13, so 2 up to 13. So remember, this is 15. Probably should write it with better penmanship. So 2, not quite to 13, so somewhere right around there. We have 3, 23, 3 up to about 25. 4, 33. Okay. 1, -17. Goodness gracious. -10, -15, and -20. Let's do light green. What the heck? Orange. Weird. -1, -17, so somewhere right around there-ish. Weird. Yeah, there we go. 0, -7, so as long as axis, 0, -7. Infinite number of solutions of points creates a solid graph. This one looks relatively linear, not completely. But let's look at some graphs. So input-output table, what I mean by that is we can construct a table. For the sake of time, we're only going to do a table with this one and recognize the patterns in like the family of functions. So here we would all agree this looks linear. And of course we would have to have coordinates. For the sake, we're just going to approximate. Let's go -1, 0, 1, 2, and 3. And let's go, let's have this be 2, 4, 6, 8, and 10. I know this coordinates are not quite linear in nature, but it's all right. So of course we have -1, 2, which would be this guy. So the coordinate we would say is -1, 2. Here we would go with 0, 4. So 0, 4. Here 1, 6. What is going on? 2, 8. Maybe I should just not switch colors other than my standard ones, but that's okay. I can just do that. And then 3, 10. So that's kind of what we're talking about when I talk about an input-output table for your homework. Here, of course, we have a parabola in shape, so it creates that nice U, so it should be symmetrical along the axis of symmetry, where they're mirrored perfectly across, which we see there. X and Y intercepts. An x-intercept where it touches the x-axis. X-intercept, x-axis. So we see right here, here, and here. So another thing to remember is that y is always 0 with an x-axis. I'm sorry, on the x-axis for an x-intercept, which is something we talked about last unit. The y-intercept, same idea, where it crosses the y-axis. Another important note is x is 0. So anytime you're looking for an intercept, you can literally just set the other's value at 0 and solve. So find all the x and y intercepts. I would say we have x intercepts here and here at what? Negative. Wow, the spacing was kind of weird on this one. It looks like -1 and 1. I'm sorry, +1. Oh goodness. Brain's fried today. 1, 0, and 2, 3, 4, 5, 6, 7, 8, 9, 0. And then the y-intercepts, so these would be x ints. The y-intercept we get is right there at -2, 0. Over here, looks like we get a y-intercept at -2, 0, and an x-intercept at 1, 2, 3, 4, 5, 6, 7, 8. 8, 0. Yeah, that makes sense because I actually have an equation for this one. So I could plug in 0 for y. So 0 equals the square root of x plus 1 minus 3. Of course, we would add 3, square both sides. So 9 equals x plus 1 minus 1 minus 1. X equals 8. Yeah, that makes sense. Here we can see that we have no x-intercepts, because we never touch the x-axis. That's okay. And we get a y-intercept at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, goodness gracious. What am I doing up here? 0, -2. I'm sorry. Goodness. On to the next one. Here's symmetry. Symmetry is when you're able to flip one polarity and they still get equal or similar results, similar coordinates. So for example, right here, 4, 2, and 4, -2 are part of this graph. The x's stayed the same, but I get both versions of the y coordinates. And if I were to actually make this into an equation, we would say it's something like x equals y squared. It's important to note that this is an equation and something you could graph, but it's not a function. So if you were to try to graph this, it's not a function because it fails the vertical line test. If you were to try to graph this, here's how you would look. You should graph it, because normally in our graphs we get y1 equals and y2 equals. I have to graph this as two separate equations. If I square root both sides, we manually square root, so I would have to do positive square root of 2, and that would give me this part of the graph. And I would also have to do negative square root of 2, and that would give me this part of my graph. Do I have my calculator? I do. So what I mean by that, oops, sorry, is I would graph them separately. So second square root x and negative second square root x. And let's go zoom 6 for zoom standard. When in doubt, zoom standard is the best way to go. You see how I get that blue part right there and that red part, as I said, the positive version and the negative version. Y-axis symmetry is when the y values stay the same, so that's 4, but I get x values to be positive and negative there. An equation like that obviously is very similar parabola of y equals x squared. You might see a pattern here with how these are set up. This other one was x equals y squared, which should make sense because conceptually, if I do -3 quantity squared, that's the exact same thing as 3 squared. So having this square helps give that positive and negative look. The origin is when both coordinates get flipped. So, for example, 2 or -2 becomes +2 for the x's, and -2 becomes +2 for the y's. A very similar equation to this is our parent function of y equals x cubed. Another very common one is like this, of y equals x. The nice thing is, the reason that they don't get the weird just one gets negative is I have not multiple. I have no even exponents. I have odd exponents. Even though these don't have exponents implied to be, a 1. So that leads naturally to how can we deduce what is symmetrical or not? Well, the best symmetry tests are as follows. If I'm able to replace the y with a negative y, and I still get structurally the same equation as I started with, they are symmetrical across the x-axis. Because remember, the x-axis says that I go from x, y, and it's equal, not arrow, sorry, equal to x negative y. The y-axis follows the same logic but flipped. So in that case, we flip the x-coordinate. And again, I get the same natural inclination. So we get this idea that xy is equivalent to -xy in terms of both being graphed. And then the other one is you actually, because you're going xy to -x, -y, you have to replace both. Both get replaced, and mathematically speaking, you end up with a -y equals -x cubed. Well, you can divide by -1 to both sides, and you actually get back to where you started. Of course, if you can't do any of these things, there is no symmetry. And that's all right. For example, a very easy one to show the no symmetry would be y equals, something like -x plus 1. Very simple line where it would look something like this. And some coordinates you would get are, for example, -1, 2. But if I plug in a +1, I'd get 0. Clearly, I can't flip the x values because my y values don't stay the same. And if I were to get a -2 for the y, that would be something like 3 for the x value. So I can't flip the x values either. So that would be non-symmetrical. Well, let's test. If you don't know, you'd have to test all three. But as I said earlier, this cube is really making me look at origin symmetry. So let's flip both the x's and the y's and see if we end up with an equivalent expression. So -y equals 2 times -x cubed. Well, -x cubed is the same thing as -x times -x times -x. So I'm multiplying 3 negatives together. The first two turn positive because negative times negative is a positive. But this is a whole positive expression times a negative expression. So this whole thing on the right-hand side is negative. So I get -2x cubed. And there's no simplifying over here, so I'm left with -y. And of course, we can divide by -1, divide by -1. Y equals 2x cubed, and that's exactly what I started with. So I was right. It's an origin symmetry. Here, I'm seeing the y is squared or has an even power. So that's the one that I would test, where I'm going to flip the y negative and see if I end up with the same expression. Negative y times negative y is positive y squared. So y squared equals 6 minus x, which is exactly what I started with. So this has x-axis symmetry. Over here, I'm seeing x with an even power, so I'm going to flip that one. So y equals 3, negative x squared plus 2. Order of operations says do the exponent. Negative x times negative x is positive x. So 3x squared plus 2 equals y. And of course, that's what I started with. So I would say this has y-axis symmetry. Okay. Thank you for listening, and I hope you have a great day.